Okay, good morning, everybody. Yeah, I'm quite happy today to present you my recent work on the novel graphical technique for pinch analysis applications and mainly for energy and mass integration. The contents of my work or my presentation, I will first present some of the challenges to chemical and refining industries, and then I will give the literature solution for these challenges, and then I will present my novel graphical technique, and I will give 2 case studies based on the time available. One mainly for energy recovery systems in a refinery plant, and one an extension of the work to a mass recycle or mass recovery system, and then I will end up my talk with a summary. Of course, all we know the challenges in chemical and refining industries, they lie into that any given chemical process or refining process, they consume large amounts of raw materials, energy, and water, providing the valuable products. And at the same time, they release large amounts of waste. And these waste are in terms of energy and water and also dissipation of materials. And if we look closer to a refining plant, we will realize that any existing refinery, it's very complex and it's very energy intensive process, and it's counted that any refinery consumes about 2% of the crude oil that is processed within that refinery. And we have a heat recovery system that is very complex, that is heating the crude oil coming from the oil well into a certain temperature, and then in a furnace where the main hot utility is consumed and then is fractionated into the several products. And for these reasons, the managers of the refining plants, they always like to reuse the existing unit without any modifications to process more capacity or to save energy or to perform any of these objectives. And of course, they prefer to achieve these objectives with minimum cost, minimum capital expenses, and also with large profit. And in order to achieve these objectives, we have different solutions in the literature, and mainly in the efficient use of material and energy. And these solutions are done through revamping projects or managing the waste, integrating the mass and energy within the plant, and also using some optimizations. The existing techniques so far to address such problems are whether we use the pinch technology or the pinch analysis technology or mathematical programming. And my new approach is based on the pinch analysis technology. That's why I will briefly present now the pinch analysis technology. I think some of you may know that the pinch analysis is a thermodynamic-based technique, and it's mainly based on two graphs, composite curves and grand composite curves, and it also includes some of the design guidelines. This pinch technology is applied mainly in energy integration or mass integration. In any of these applications, it will give you the energy targets, the minimum energy that you need or the minimum material that you need, and also it can produce the optimum exchanger network, whether for energy or for mass. So this is the application of pinch technology. And as a very simple example, if you present any existing refinery, you can combine all the process heat sources and the process heat sinks in a one graph for hot composite curve and one graph called cold composite curve. And this is the temperature versus heat flow. So this graph is very typical for any existing process, and the shortest distance between the two curves is called the pinch. And this is where the name of pinch technology comes from. So this is the pinch, and the pinch point divide the process into 2 sections, one above the pinch, this way, and one below the pinch. And as a very simple application, if we use the pinch technology on such a process, this is an existing pyridine process. It's a chemical compound. Pyridine is used in agrochemical and pharmaceutical industry. This existing design tells us it consumes 9.1 megawatt of hot utility and 30.4 megawatt of cold utility. And if we apply the pinch analysis on that case, it will tell us this process, if it was properly designed, so it should consume 1.4 megawatt instead of 9 in hot, and also 9.3 instead of 30 megawatt for cold. And this is easily obtained by pinch technology. But what we cannot obtain from such figure or from the pinch technology are these. We cannot tell why the process performs so poor and why or where the energy inefficiencies are located in that figure, and also how can we modify the process or can improve the energy integration. And this is the main limitation of the pinch technology as graphical based. And if the problem even becomes more difficult if we look at an existing refinery. That refinery is Nynäs refinery in Sweden. So if we want to improve that, look at the preheat train or the heat recovery system, it looks very complex. And pinch technology also tells us that this process consumes existingly 6.4 megawatt, although the energy target 3.7, so it's almost consuming double of the energy. And again, the pinch technology cannot tell more than this. That's why I summarize my motivation of the work. There should be a new tool or technique that is simple and requires no software. Of course, all these previous problems we can solve using software, but very expensive software. And it can provide us with an interface or visualization feature. And this technique can be applied for mass and energy integration. And this is my new method. In my method, I simplified an existing exchanger unit as two streams, one hot streams and one cold streams. And for this stream, for this exchanger, I calculated the mass and energy balance for these two through the hot stream and the cold stream, and these two equations. And then if I divide the two equations, I get relation between the heat capacity flows and the temperature difference among this exchanger. And this tells me if I plot the temperature of the hot versus the temperature of the cold, I can easily represent that exchanger unit through a straight line. This straight line is bounded by the hot stream and cold stream. The length of this line, I found it's very proportional to the duty. So the heat transfer rate across that exchanger is proportional to the length of that exchanger. And this is the equation for calculating the Q. So the line, so we can present any exchanger unit using only simple straight line bounded by hot stream and cold stream, and the length of this stream is equivalent to the duty. So on the graph of temperature hot versus temperature cold, I can easily plot the hot temperature pinch and cold temperature pinch. And then I have four regions. And if I plot the thermodynamic equation or limitation that gives us the temperature of hot is equal to temperature of hot, then I have 5 regions, different regions. Below that line is infeasible, and this region here is optimum heat recovery. This region there also is optimum heat recovery. These two yellow regions are not optimum heat recovery. So we can easily detect that for any given process, any given heat recovery system, if I can have all my exchangers within that quarter and that region, then I have optimum heat recovery problem. I should not have energy here, I should not have energy there, and I should not have energy transfer within this limit. And on that curve, the straight line represents an exchanger unit. The distance between the line and the diagonal represents the temperature driving force. So the shortest distance means that this exchanger is limiting the heat transfer. So if this exchanger, for example, is touching the diagonal, this means I have zero temperature difference. And this tells us that this exchanger is limiting the heat recovery. And if I can move that exchanger from one place to another, then by resequencing, I can move horizontal direction. On that graph, I can also represent any hot stream as horizontal line, and any cold stream as vertical line, and the overlap within these two streams represent the heat recovery within that part. So I can maximize the heat transfer between these two streams, the hot stream and the cold stream, represented by this black line. So this line represents the maximum heat transfer accomplished within that region. The more features of that approach, it's very simple. As you see, it's very simple. It's only based on graph, piece of paper and pen, and you plot temperature hot, temperature cold. It's very simple, and it has user visualization, so you can see what you are dealing with. The performance of the network can be interpreted that if I have exchangers within that figure, then I have optimum heat recovery. And in revamping, we will see now in a case study, we can perform the revamping or modifying an existing plant. I applied that graphical technique on a case study. This case study is an atmospheric unit with vacuum unit processing 85,000 barrels per day of crude oil. The existing hot energy required is 80 megawatt, so this plant consumes 80 megawatt energy, and cold energy 35.5 megawatt. This is the existing unit, and this is the existing heat recovery system or the existing preheat train. So as you see, this is the crude oil heated in a number of exchangers till entering the tower at 343 degrees. From the pinch, the basic pinch technology, we can easily say that this energy, the minimum energy is 64 megawatt. So this process, if it was properly designed according to the pinch, so it should have consumed 65 megawatt, not 85 megawatt. But nothing more. The pinch technology cannot tell us more than this information. If I plotted my graph on that case, look how is it configured. This is the hot pinch and the cold pinch. Look at all exchangers are here and some are here. And look at this quarter, the region for non-optimum heat recovery. It contains 3 exchangers, 3, 4, 5, and even 1 cooler. So, and you can expect that if you remove these exchangers from the existing network, then you can improve the design. And the process, the graph also proposes some modifications. And these modifications are removing this exchanger 3, 4, 5 from that quarter and bring them here, and also reduce the heat load on that cooler. This cooler, part of the cooler is lying in that region, which is not optimum. And also this line and this line, the blue and black, the blue is longer than the black, which means I cool more than I integrate heat. So it's better to move these exchangers and also increase the length of this black line at the expense of this blue line. And once I have done this, look at this. This is the modified network. This is exchanger 4, and now is here. Where is it 4? 4 somewhere here. 3 is here. 5 should be there. So I removed 4, 3, and 5. I moved them, and I increased the length of exchanger, the small one, and this is the new location, and this is the old location, and this is the new location. And I added 1 exchanger unit to take part of this cooling duty. And as a result of this, I reduced the energy up to 66 megawatt. So I saved 13.5 megawatt saving of hot utility, and it's worth of $2 million per year, saving by moving these exchangers. So now look at this, the new network. There is no more exchanger within this area except this small one. And exchanger 3 is here, 4 is here, and 5 is here. And this is the new exchanger unit, and this is the new exchanger unit. So look at this, the benefits. And this is the optimum network produced. And these are the results of the case. The hot energy is reduced by 17%, and the fuel consumption reduced by 12,000 tons per year, and the energy cost saving is almost 2 million pounds per year, and also the carbon dioxide emissions are reduced within the same value. An extension of that work was done to mass recycle or mass integration, and I found I could also plot the same graph for mass, just in terms of composition of rich versus composition of lean streams. And again, I could also plot the hot pinch and the cold pinch. Just 2 minutes, I will finish. And again, any exchanger unit can be represented by a straight line in terms of mass, plotted between these compositions, and the length of this composition is proportional to the mass transferred across that. And as a case study, this is the case study, a plant providing a gas stream containing benzene to the atmosphere with that composition, although it should be 0.1 as environmental limitation. And I used the same graph to design the network. This is the graphical design, and this is the design that is produced. And look at the savings. External utility saving 52.6 and 58.8 waste minimization. And in summary, the graphical technique is very simple and developed originally for energy. It can evaluate the performance of any heat recovery system. It is very easy, very simple, and it is user visualized based. It requires no expensive simulator, no simulation packages, and it can be used actually for academic teaching. And this was my presentation. And just if you are interested to see the network for the Nynäs refinery of Sweden, look at it. And again, you see, it contains more exchangers within that area. And these are the 3 publications recently published on that work. And I would like to thank you all for your attention. Thank you.